In this video, we are going to learn concept of Cox proportional hazard regression. And I have a separate video showing how to conduct Cox regression in SPSS. And there is additional video to talk about advanced topics in Cox regression, which include Cox with time-varying hazard ratio and also Cox model with time-varying covariate. In the chapter of logistic regression, we talk about several measures of association. So if you are interested in computing odds ratio, choice for regression is a logistic regression. And if you want to compute relative risk, and there is a regression, and you can compute the relative risk. And although the popular choice of regression for binary outcome data is a logistic regression. And if you have a time to event data, and you could compare rate of two groups instead of just the proportion or odds of event. So you could do rate ratio, and choice for regression is a Poisson regression. And today we do have a similar data to analysis we conduct Poisson regression. So we know the data on who had and who didn't have events binary outcome. And we also know time one event occur, so time to the event. And the measures of association, which is very similar to rate ratio, is we have a hazard ratio. Okay? And if you want to do analysis with a hazard ratio, and Cox regression is a typical choice for regression. Okay? And an important thing I want you to remember is when you have odds ratio, you can't really imply risk anymore. So risk is quantified by proportion of events or probability of events or rate or hazard. And odds are actually mathematically different from those proportion or rate or from hazard. So we cannot use word risk. We can't really imply risk based on odds ratio. But using rate, using hazard, yes, now we can imply risk. So let's say if you have a hazard ratio of 2, and yes, you can say risk increased by twofold. And the analysis by Cox regression is very similar to that by the logistic regression. So SPSS screenshots or common SPSS options or comments for analyzing these two models are very similar. So I think if you know how to conduct logistic regression, and nothing is difficult to conduct Cox regression. And a key difference is how we interpret the coefficients. So in logistic regression, the model coefficient estimate log of odds ratio. So we exponentiate the beta, and that gives odds ratio. And with the Cox regression, beta coefficient estimate log of hazard ratio. So when you take exponential of beta, and you have a hazard ratio. Okay? So interpretation is a little bit different because we have a different choice for measures of association. Although comment in SPSS is very similar. So let's review what is a hazard then. And we did talk about hazard when we studied Kaplan-Meier curve. So let's review what is the concept of a hazard. And a hazard is instantaneous risk of dying. So for example, so if you have a person here, okay, so this person have a probability of, okay, in dying 10% every day, okay, and then we follow this person over time, and this is days, and this is day 1, day 2, day 3, day 4, and day 5, and day 6. Okay, and this person every day have a chance of dying at 10%. So what is, okay, so every day. So here you have 10%, this person have 10% risk of dying. In day 2, this person have 10% risk of dying. In day 3, this person have 10% risk of dying. Okay, so in this case, hazard is instantaneous risk of dying. So which is 10%. Okay, So when you have a daily hazard constant of 10%, let's compute cumulative probability of survival for this person. Okay, so let's say cumulative of survival at end of day 1. Day 1. Okay, so that is 1 minus hazard. So 0.1 is the probability of dying this person for day 1, so which is 0.9. So let's compute cumulative probability of survival. What is the probability this person survive at end of day 2? Is 1 minus 0.1, which is a hazard, right? And times 1 minus 0.1. So this is the probability of this person survive at day 1, and this is the probability of this person survive at day 2. And in order for this person to survive at the end of day 2, this person have to survive at the end of day 1. So you have 0.9 and 0.9, and then you multiply this and you get 0.81. Okay, and the same thing, the probability of this person surviving by the end of day 3 is 0.9 to the power of 3. Okay, so this is about 0.73. Okay, so if you plot this probability on Kaplan-Meier graph, and you don't really have a linear decrease in cumulative percent of survival. So you start with 1, everybody survive, and then day 1 it become 0.81, 0.9, and then so that's day 1, and then day 2 that become about 0.81, and then day 3 it become 0.73. So if you connect this probability, you have a curve slightly bent, and it's not exactly the linear decrease. Okay, so let's do the same thing, and if to compute the same thing when your daily risk of dying is 20%. Okay, so by the end of day 1, your risk of death is 0.8. By the end of day 2, your risk of dying is 0.8 to the power of the 2. So you have 0.64. And then end of day 3, and your risk of surviving by the end of day 3 would be 0.51. Okay, so if you connect this cumulative probability, which we need for Kaplan-Meier graph, and day 1 you have 0.8, day 2 you have 0.64, and then day 5 you have 0.51. So you have a curve and bend like that. Okay, and so hazard is a constant this case. So this graph is when daily hazard of dying is 10%, and this graph is when daily hazard of dying is 20%. Okay, and then what we have on Kaplan-Meier graph is a cumulative probability of survival. And let's look at next slide. So this is a better looking graph than my handwriting. So when you have a daily risk hazard of dying at 10%, okay, and this red line, so you have a constant hazard of 10%, and then this translates into Kaplan-Meier graph, which looks like this red line. Okay, it's slightly bent. It's not exactly a straight line. And then if you have a daily risk of dying, which is a hazard, constant hazard of 20% every day, and then this convert to this green line of a cumulative probability of survival. Okay, and then if every day you have very high risk of dying, 80% of risk of dying every day, and then it convert to this purple line. So that is a cumulative probability of survival. Okay, and so what we need to be careful is cumulative probability of survival, which we are looking on Kaplan-Meier graph, is not really straight. So So even when the risk is constant and we expect slightly curved linear decrease in survival curve. And when you have a very sick population and everybody died, and eventually, and the curve reached to 0%, but it doesn't go below 0%. So the reason I emphasize to differentiate hazard versus cumulative probability of survival is Cox regression, and we are estimating hazard ratio. Okay? So we do think about this instantaneous risk of dying. So what if the person have a risk of dying of 20% every day, and then we convert hazard to a Kaplan-Meier graph, which we have a cumulative probability of survival. So these two concepts are very important to understand. In a Cox proportional hazard regression have important assumptions, which is called proportionality of hazard. So the proportionality of hazard is, let me explain the concept with the next several slides. Okay, so let's use this for example to learn what is the proportionality of a hazard is. Okay, and let's say that this graph, and you have, let's say this is a graph for new drug. It's a drug, and this is a placebo. So without the drug, and every day patient have risk of dying of 30%. And with drug, and you have risk of dying as low as 10%. Okay? And so here you have 10%, 10%, 10%, 10%, 10%, 10%. Here you have 30%, 30%, 30%, 30%, 30%, 30%. Okay? And hazard ratio is a ratio between two hazards. So in this case, if you compare this point, hazard ratio be 3. Hazard ratio be 1/3. So you can say there is a risk reduction of death by 67%, because this is 33%. 1 minus that is 67%. And when you look at here, okay, hazard ratio would be 1/3. So there is a 67% risk reduction by using this drug. So this means hazard ratio is constant, right? And then let's look at this graph. In this graph, and we have strange looking hazard. Okay. So the beginning of the study, let's say this is a drug group, and this is a placebo. In beginning of the study, and everybody, both drug and placebo, has lower risk. And then the middle of the study, risk accelerate. And then toward the end of the study, and you have a stabilized risk. Okay. And so risk is changing. It's no longer constant, like this example. Also, if you compute the ratio between these two risks, say here, daily risk of dying would be as low as 10%, and this group is as high as 0.3. Here you increase daily risk of dying is 20%, and here you increase it to 60%. And then this got stabilized to, again, 10% and 30% here. And then if you take a ratio between two hazard, and hazard ratio would be, okay, let me use a pen, 1/3 here. And then this point, and the hazard ratio would be 1/3. And then here, this point, and the hazard ratio would be 1/3. So even when you have a changing hazard, as long as the degree of change is similar, and you can have constant hazard ratio. That means hazard ratio can be similar in whichever the time points you look. Okay? So when we say hazard are proportional, that means hazard ratio is constant. Hazard are proportional. This is the same thing as hazard ratio is constant. Alright? So what if you have and hazard of each group is constant over time? So you have two groups, okay, and each group and you have constant hazard. So the graph, Kaplan-Meier graph looks like this. Okay, so constant hazard, two groups hazard are constant, and that means hazard ratio is constant, which is the same as hazard is or proportional. Okay, so when you have changing hazard, okay, so weird looking survival graph, but another group is also weird looking. Weirdness is similar, and then you can still have constant hazard ratio. Alright, so in this case we still have hazard, so proportional. Okay, and how about the next example? And you have two survival curves crossed each other. Okay, so placebo groups actually have a constant hazard. Okay? But then when you operate patient and they have a high mortality rate begin with, but then once they survive at some point and risk stabilized. Okay, let me rewrite again. So you have a constant hazard for placebo, but then with operated patient, and you have changing hazard like that. So when the two Kaplan-Meier graph cross over, and you no longer have proportional hazard. Okay, the Cox regression require these two scenarios. Hazard have to be proportional, which means if you compute hazard ratio at any point of time, and hazard ratio should be constant, right? And assumption get violated when you have a situation like this. And how about, okay, let's look at this example. And here, with the drug group, okay, and people who use a new drug, and then this is a placebo group, and a hazard ratio here with a drug maybe as low as 10%, and then placebo group you have a steeper slope, so hazard could be as high as 5. So if you take a ratio and you have 1/5 is a hazard ratio, and then if you look at the middle point, and then slope of these two survival curve looks similar, so hazard ratio could be 1 at this point. And then here, if you look at here, and you start seeing accelerating risk with the drug group, and then the slope is actually lower with a smaller with the placebo group. So hazard ratio in this case could indicate higher risk by a drug. So here you have 1/5 as a hazard ratio, and 1 and 3. So this clearly look hazard are not proportional, i.e. hazard ratio is not constant over time. So Cox does not work well in this case. Okay, and this is a situation to survival curve crossover. So in this case, Cox does not work well. Okay, so what do you think about this graph? So this is actually 23-year result or 22-year result of this CABG trial. Okay, one of the 3 biggest CABG trial in the world. So let's look at the graph. So blue is a medically treated patient, and then a green line is treated with CABG. Right? So up to let's say 11 years, and green line is actually above blue line. So that's indicate benefit by CABG, right? So if you compute hazard ratio, and a hazard ratio is probably less than 1. Hazard ratio is less than 1, and indicating reduction of death by CABG. But if you look at here, okay, And the cabbage group actually have worse survival and then the medically treated patient. So hazard ratio could be greater than 1, indicating increased risk of dying by surgery. Right? And so when Kaplan-Meier course is over, and that clearly indicates changing effect of a drug, or this time it's surgery. Okay, so you cannot really assume hazards are proportional. So if you go ahead to apply Cox regression, and then and this is what you get in the result. So let's say hazard ratio exponential of beta is 1.11, and that indicate 11% increase of risk of dying, and as an average over 23 years or 22 years. Okay, there is a risk of 11% increase in risk of dying by cabbage. Okay, and although it was not statistically significant, but you are facing a cabbage not being effective. And is that true? And it looks like cabbage was working up to some point, and then it stopped working after that point. And so what point do you think cabbage start not working? Okay? And you think the point in Kaplan-Meier courses, and or how about this point here? You have a risk start changing somewhere here, and then here slope is actually steeper. So it looks like the risk of dying start accelerating at around 7 years. Okay, and that's actually when many patients start getting a second operation because original graft got closed. So they have to have a second operation. And then this study was conducted early 1970s. So it's a very old study. And then that time at the VA, and the operational mortality with the second cabbage was as high as 11%. So that's actually added accelerating risk in the cabbage population. So for the Cox regressions, and we do check for model assumption, which is a proportionality of a hazard. And data like this, and you can simply eyeball Kaplan-Meier graph and then judge whether the effect seems changing over time or not, hazard ratio is constant or changing over time. And so by quick eyeball check, and you can see there's a violation of the proportionality of a hazard. But if you have data like this and judgment is not that clear, and you want to have some diagnosis tool which help you to judge whether a proportionality of a hazard assumption is met or not. Okay, and there is a method you can use which is called the log-log plots. Okay. And so let me show you how to use log-log plots. All right. So this is a data set of cabbage. So here we don't use 6-year outcome. Instead, we are going to use 22-year outcome. So let's do Cox regression. So you go to survival and Cox regression, and serve year is a time, and status is a binary status variable, and then we tell SPSS, we call the death as 1. And we want to see effect of cabbage, and variable for that is a treatment. So you put it under covariate box. It's a 0-1 coded, so you don't have to worry about categorical box, right? And right, let's go ahead to perform Cox regression. And a Cox regression gives you just one hazard ratio. So this is average of the ratio of a hazard over 22 years. So by average, and you say 11% increase of risk of dying by cabbage, although it was not statistically significant. Okay, but by doing Kaplan-Meier graph, so now we go to Kaplan-Meier, and serve year time, and status is status, and put 1 here. and treatment goes to under factor, and we want survival graph. Okay, and let's disable this table. And right, so this is a Kaplan-Meier graph. And so it's actually a wrong statement, and you say the risk of dying by cabbage is 11% larger, because clearly there was a time point or interval and cabbage was working clearly. Right? And so let's check if this model, the result you have hazard ratio 1.11 is valid or not. And if you can't really judge effect of changing over time based on this Kaplan-Meier graph, okay, so you go to Cox Regression. So go back to Cox Regression, right? And then now you click on plots, right? And then click on log minus log. Right? And when you do that, important things you have to remember is remove treatment under covariate box and put it under strata. Okay, that's very, very important to remember. So put the treatment, cabbage versus medical therapy, under strata. Okay, and then go back to plots and click log minus log plots and continue and OK. And then when this log plots, okay, so y-axis is log minus log of cumulative survival probability, okay, and then x-axis is years after randomization. And in order to have a proportional hazard assumption being met, you need to see parallel lines. Okay, so what the parallel line means? So what the parallel line means is a graph looks like this. Okay, so it does look parallel, and the graph we have, right, and lines are clearly crossed over, so it's not a parallel. So when the effects are clearly changing, and we can no longer use general Cox regression model anymore. Instead, and we use the Cox model, and which can detect time varying hazard ratio, which means time varying effect of the treatment. Okay, and this is for another video. And thank you so much for listening, and I see you at the next video. Goodbye.